Hello and welcome to the Data Revolution podcast, where we explore the frontiers of data, its impact on our world. I'm your host, Kate Carruthers. AI is an exciting and terrifying technology all at once. Now, I'm not one of the doomsayers who say that AI is going to kill us all, but at the same time, there are notable downsides as well as upsides to this technology. For example, there are environmental impacts of the huge data centers required, the implications of the large-scale theft of everybody's intellectual property that underlay these models, and the threats to mental health, jobs, the economy, capitalism, and societal well-being. Now, we're going to cover these issues in other episodes, and like all technology, this one holds great promise for human progress in the right hands. And today we're going to look at some of the history of how we came to be in this place. In my recent chat with the amazing Leonie Valentine, I realized that I had said something about Google and AI that could be misconstrued. I was being critical of their consumer offerings in the realm of AI, which I do believe they have been slow to the party on these, and I'm often critical about their consumer and business products. But I thought it worthwhile to share some of their history with AI because they have been one of the engines behind the growth and research that has made AI what it is today. For the past decade, one company has been at the epicenter of a major shift in artificial intelligence, quietly building the foundations for a new technological era. That company is Google. From the algorithms that power our daily searches to significant scientific discoveries, Google's AI has become an invisible yet indispensable force. Now, today we're going to take a deep dive into Google's AI journey over the last about decade. We'll look at some of the pivotal moments, some of the important breakthroughs, and the ambitious vision that is shaping not just the future of technology, but also aspects of the future of technology. So let's get into it. Our story starts around 2015, when AI was still mostly a research topic rather than something you would see in everyday products or in boardroom slide decks. That shifted when Google released TensorFlow as an open source product. Think of TensorFlow as a general toolkit for building AI systems rather than as a single monolithic product. By open sourcing it under an Apache 2 license, Google did not just release some internal code. They put industrial-grade machine learning infrastructure into the hands of anyone with a laptop and an internet connection. Developers and researchers all over the world suddenly had access to the same class of tooling that powered Google's own system, which dramatically lowered the barrier to doing serious research in machine learning. Now, they also liberally sprinkled credits to use their platform out to researchers. So researchers were not even having to pay for the compute, which was a big thing, and researchers are always hungry for free compute. Now, this was not just greenfield code written for show. TensorFlow came out of the Google Brain team, and it had already been used in production across core products before it was opened up. Making that stack publicly available was a turning point. It allowed the research community to build on a shared platform instead of reinventing it in isolation, and it helped accelerate the pace and scale of AI experimentation. Now, TensorFlow also landed in a landscape where other open source frameworks were already doing important work. Products like Theano and Torch had been around for years, and shortly after that, PyTorch would gain traction, particularly in research and prototyping. Taken together, these tools helped to move AI from something esoteric and niche into something that was more accessible to a much broader community. And then there was the DeepMind acquisition. So this is something where we need to go back to 2014. This was a pivotal year when Google made one of its most consequential moves in the AI space. In January 2014, Google acquired DeepMind. They were a London-based artificial intelligence startup, and they acquired it for more than $500 million US. This was Google's largest European acquisition at the time, and it would prove one of the most significant strategic bets in recent history. DeepMind was founded by the neuroscientist Demis Hassabis, a former child chess prodigy, along with Shane Legg and Mustafa Suleyman. The company was focused on building general-purpose learning algorithms that could tackle complex problems in games, in simulations, and more. By acquiring DeepMind, Google was essentially betting big on the future of deep learning and AI intelligence research. This acquisition brought together Google's massive computational resources and infrastructure together with DeepMind's cutting-edge research capabilities. This partnership would go on to produce some of the most significant AI breakthroughs of the past decade, and it fundamentally shaped the trajectory of AI development globally. It was 2 years later, in 2016, that Google delivered a moment that attracted global attention, AlphaGo. This was the ancient game of Go, which has an astronomical number of possible moves and it had long been considered a grand challenge for AI. Google's DeepMind division developed AlphaGo to take on that challenge. AlphaGo faced Lee Sedol, one of the world's top Go players, in a 5-game match. It was watched by more than 200 million people, and AlphaGo won 4 games to 1. Commentators describe some of its moves as creative and even beautiful, and they showed that AI could demonstrate strategic patterns that could even surprise human experts. Behind the scenes, Google was also building hardware to power this shift. In the same year as the AlphaGo match, they unveiled their Tensor Processing Units, or TPUs, which are custom-designed chips built to run machine learning models efficiently at scale. While CPUs and GPUs are generalists, TPUs are specialists, and their development gave Google a substantial advantage in training and deploying large models. Then in 2017 came the breakthrough that would become the architectural backbone of most of the current generation of AI, the transformer. A Google research paper titled "Attention is All You Need" introduced this new neural network architecture. Before the architecture of transformers, AI models struggled to handle really long-range context in language. The attention mechanism allowed models to weigh different words in a sequence, regardless of their distance from each other. And this became the key idea that underpins modern large language models. This innocent little paper, "Attention is All You Need," was a catalyst for a huge amount of subsequent work. Much of what comes after in the story of language models hinges on it. This paper was written by 8 Google researchers. I'm not going to try and pronounce their names. The authors are listed in random order as a signal of equal contribution, and all 8 later left Google to pursue other inventions, including founding startups. The title's a nod to the Beatles song "All You Need Is Love," and the team informally referred to themselves as Team Transformer. The transformer architecture introduced self-attention, multi-headed attention, and positional encoding as core components. Self-attention allows the model to weigh the importance of different tokens when processing a specific token. Multi-head attention enables the model to look at different representational subspaces in parallel, and positional encodings provide information about the order of tokens. Together, these mechanisms underpin most contemporary large language models. And then, armed with the transformer, Google began to reshape its own product. In 2019, they integrated a model called BERT, which was the bidirectional encoder representations from transformers, into Google Search. BERT allowed search to understand the full context of a query rather than just isolated keywords, and improved the relevance of many search results. Beyond search, DeepMind announced a major scientific result in 2020, AlphaFold. For 50 years, scientists had been grappling with the protein folding problem, predicting the 3-dimensional shape of a protein from its amino acid sequence. AlphaFold achieved highly accurate protein structure prediction. The team then released structures for more than 200 million proteins into a public database, which opened up new possibilities for work on vaccines, treatments, and enzymes that can break down pollutants, among other areas. It's a prominent example of AI being applied directly to scientific and medical problems at scale. And this is one of the things that Google often does. They often release their stuff publicly, unlike other vendors who don't do that. There are some who keep their stuff very proprietary and locked down, and it limits the benefit that can be developed from it for the world, which is kudos to Google for doing this. Meanwhile, another group at Google is working on conversational models, and this led to LaMDA, the language model for dialogue applications, which helped pave the way for the generative AI wave that followed. And we come now almost to the current day with the launch of OpenAI's ChatGPT, which was launched in late 2022, and it drew global attention to conversational AI. Now, Google's response was something called Bard, which was released in March 2023. It was an experimental conversation system, initially powered by LaMDA and later by Palm 2. Now, when Bard arrived in early 2023, it landed with a complete thud rather than a bang. It was explicitly framed as an experiment, a companion to search, and not fully integrated flagship product. And the launch was not helped by a demo error involving the James Webb Space Telescope that attracted substantial media coverage and market scrutiny. Early users and reviewers reported hallucination, uneven reliability, and researchers even cautioned against uncritical use of Bard in medical or academic work. In day-to-day use, Bard could handle straightforward tasks such as light brainstorming, short writing, and simple recommendation, but it generally felt a step behind some rivals on reasoning and factual accuracy. Commentators noted that Google appeared cautious, limiting how deeply Bard was integrated into core search and productivity workflows. You wonder if there might have been a reason for that. But in December 2023, Google unveiled Gemini, which was a new family of multimodal models that were designed to work across text, images, audio, and video. And in 2024, early 2024, it was rebranded as Gemini, bringing all of Google's public-facing AI efforts under a single label. Now, later iterations such as Gemini 2.0 and Gemini 2.5 Pro have focused on what Google describes as more agentic behavior and improved reasoning and coding capabilities. And these underpin their new experimental systems like Project Astra and Jules. Jules is an AI coding agent. This is all interesting, but Google's done more. They've done more. In search, Google's Search Generative Experience, SGE, integrates generative AI summaries into results. Now, some people hate this, some people love it. I'm ambivalent. But this provides overviews rather than only lists of links. In healthcare and biomedical research, models such as AlphaFold and MedGemini are being explored for tasks ranging from image interpretation to diagnostic support and screening. Google is also working on AI for scientific discovery, including systems that act as AI co-scientists that help to sift literature, propose hypotheses, and suggest targets in drug discovery and related fields. To make all of this possible, Google has invested significantly in research, in infrastructure, and governance. In April 2023, nearly a decade after acquiring DeepMind, Google merged Google Brain and DeepMind into a single unit, which is called Google DeepMind and is led by Demis Hassabis, the founder of DeepMind. They've also invested heavily in custom TPU chips, which are now in their sixth generation, known as Trillium. The broader ecosystem now includes a whole lot of different chipsets, and I'm going to explain those just so you can understand what they do. The broader ecosystem now includes CPUs for general purpose work, GPUs for parallel numeric computation, and DPUs for data-centric infrastructure tasks, and TPUs, which are specialized for deep learning workloads. I'll cover off those in specifics in a minute. But this decade of innovation has been guided by Google's AI principles, and they were one of the early vendors to publish their AI principles. They published them originally in 2018, and they commit the company to aims such as social benefits, safety, and accountability in AI development. Now, coming back to the difference between GPUs, so CPUs, central processing units, they're what we all have in our normal computers and servers. They're just the general workhorses of the world that we use in computing. GPUs are graphics processing units, which are used mostly for AI now. They're large-scale parallel operations. And DPUs are data processing units, which are actually used to offload work from the CPUs and GPUs to do networking-style tasks. And it's interesting that a lot of this specialization in chips has actually been driven by a lot of the work that Google has done. So it's been an interesting decade for them. So you can see that Google's role in modern AI has been significant, from the acquisition of DeepMind in 2014 through to the open source release of TensorFlow, the AlphaGo milestone, and now multimodal agentic systems like Gemini. Its work has helped to shape the field and many of the tools we now take for granted. Over the past decade, these systems have changed how we search for information, how we approach some aspects of scientific discovery, and how we think about diagnosing and treating disease. They have also provided many of the underlying building blocks that others now use to create new applications and services. The next decade is unlikely to be about hype, though. It's more likely to be about ongoing integration with AI systems moving from experimental demos into infrastructure, workflows, and everyday tools. Some of this will be useful and very ordinary, and some of it will raise new risks and governance challenges that we are only beginning to understand. This will take us into unexpected territory for good and for ill, and it will require careful navigation by boards, policymakers, and operational leaders who are not always technologists, but who are always accountable for outcomes. Anyway, thanks for tuning into the Data Revolution podcast. I'm Kate Carruthers. Please join me next time as we unpack what these changes really mean for organizations and the people who run them.